Hello and welcome to Lecture 2D. In this lecture we're going to be looking at electron configuration. We're going to start off by defining what an orbital is. An orbital is a representation of the space occupied by an electron in an atom. It's the potential space for an electron. The edges of an orbital are fuzzy. There's not a definite edge to these orbitals. It does not have a definite or an exact size. Chemists arbitrarily define an orbital size as the space that contains 90% of the total electron's probability. So this is where we're 90% likely to find an electron. And then the ground state is an electron's lowest energy state. So what does an orbital look like? Well, this just kind of gives us an idea of what an orbital might look like. So we have those smaller orbitals, and it's built up from there, and these dumbbells or other ideas of where we might find these electrons at. Alright, the principal energy levels we label with the integers. For the S and P sections of the periodic table. This corresponds to the row number. So, for example, the first row is 1, second row is 2. We have sublevels. Each principal energy level is subdivided into smaller sublevels. We've got an example on page 334. It's an inverted pyramid that kind of shows how these sublevels are figured out. We designate these by the letters S, P, D, and F. Each sublevel consists of one or more orbitals, each of which contains 2 electrons. So if we look at a periodic table, we would identify these first 2 columns as the S block, and we would include helium. Could stick it right here next to hydrogen. That's all S block. And then when we start writing these electron configurations, we go from S to P. So these 6 columns are the P block. D is this section that's set in the middle here. So we'd actually go S to P to D, and then finally to the F block, which is this bottom section. An S sublevel has 1 orbital. It can contain up to 2 electrons. A P sublevel has 3 orbitals, and each orbital can contain up to 2 electrons, but the P sublevel overall can hold up to 6 electrons total. A D sublevel has 5 orbitals. It can hold up to 10 electrons, and an F sublevel has 7 orbitals holding up to 14 electrons. So when we label these orbitals, the number tells the principal energy level, the letter tells the shape of the orbital. So the letter S means it's a spherical shape, the letter P indicates that it's a 2-lobed orbital, and then when we look at the next slide here, we'll see an X, Y, and Z subscripts on the P orbitals, which coordinate with the axis that we find these orbitals on. So they can't lie on the same plane, so we're just labeling those planes here. So our first S orbital is this little sphere. Our 2s orbital is going to be a sphere also, but it's larger. And the 1s orbital would actually be contained within the 2s orbital. And then from there we get the P orbital, which is actually these 3 dumbbells superimposed upon one another. So they all meet where the dumbbells pinched off, but they're going to be on different planes. And then the D has this kind of double dumbbell shape, and they all kind of intertwine with one another as well. Alright, so some information about electron configuration. The number and arrangement of electrons around the nucleus of the atom determines its chemical properties. Therefore, it is useful to be able to determine and write out the electron arrangement, which we call an electron configuration. The electron configuration of an atom is written by stating the number of electrons in each energy sublevel and writing the sublevel in order of increasing energy. It's kind of like our electron's individual address. So the number of electrons and energy sublevels indicated by a superscript integer. So if we look at hydrogen, our first number is the row that we're in. So we have 1. Actually, it's the energy level, but for S and P, it happens to be the row. So for hydrogen, we're in this first row. So we're 1. Find hydrogen here where I have my cursor. This is the S section or S block. And we only have 1 electron. When we go to helium, we're in the first row still. We're in this first energy level. We're still in the S block. So we just imagine that the helium is technically sitting here next to hydrogen. So our first energy level, still in the S block, but now we have 2 electrons. So that's what the superscript 2 indicates. We've got some governing rules for electron configuration. We've got the off-ball principle, which says that each successive electron occupies the lowest energy orbital available. So electrons are kind of lazy. They like to take whatever lowest possible energy they can use, and they stick to that to start off with. We have the Pauli exclusion principle, that only 2 electrons can fit in an orbital. When 2 electrons occupy the same orbital, they spin in opposite directions. And we say spin, it's kind of arbitrary though. Basically they're going in opposite directions. Because they do have the same charge, they can't be going in the same direction. Then we've got Hund's rule. When electrons have a choice of entering 2 equal orbitals, they enter the orbitals so that a maximum number of unpaired electrons results. So we'll look at this more in detail when we start writing out orbital diagrams. But an orbital diagram is orbitals are represented by boxes grouped by sublevels with small arrows indicating the electrons. So if we look down here underneath our diagram, we've got these little boxes. So 1s has 2 electrons. We show those with arrows going in opposite directions. So one spinning one way, one spinning the other. Our 2s orbital, we have a little box, 2 electrons spinning in opposite directions. And our p orbital, well, we've got 6 total electrons, but notice we've got 2 electrons in each box, and within each box, or each orbital, they're spinning in opposite directions. Alright, so you're probably wondering, okay, what's this going to look like on my homework or for an assignment? So let's look at that then. So let's start off by looking at hydrogen, helium, lithium, and beryllium. So with helium, I'm again in this first row, or this first energy level. So I start off by writing 1. It's in this S block, so I'm going to write an S. And I only have 1 electron, so I write a superscript 1. And this over here is my orbital diagram. So I'm going to draw a line to indicate that I'm in this first S. And I only have 1 electron, so I'm going to draw an arrow. And in my case, I tend to only draw 1/2 of the arrow point. If you want to draw the other half of the arrow point, that's fine. But when you look at my examples, I'm only going to have half of the point of the arrow. Our next example is helium. And I'm in my first energy level. I'm still in this S block, but now I've got 2 electrons. So I'm going to do my orbital diagram with the arrows pointing in opposite directions. So basically I'm just adding an electron. So notice my electron address is different by 1 electron when I go from helium, or go from hydrogen to helium. So I'm just adding an electron when I go across. So I'm just adding an arrow. It's going in opposite directions. Alright, on this next slide, I've filled in both sides of the arrow. So if you feel more comfortable with that other side, go ahead and fill it in. But with lithium here, I am going to build this up. So because I filled this first energy level with helium, I now have to go to my second energy level. So I have to build from there. So I have 1s2, which filled this first energy level, and now I'm on the second energy level, or second row. Lithium's here under my cursor. I'm in the S block again, and I'll have one additional electron from my previous row. So if I count the superscripts, I have 2 for my first row, and now I have a third one. So I have 3 total electrons. And when I write out my orbital diagram, I keep my helium one, and I add another S block and my additional electron. It doesn't really matter whether you start off by pointing these up or pointing these down. I do tend to go up with those though. Alright, beryllium. I'm keeping my 1s2 from my first energy level. I'm just building onto my second energy level, and S can hold 2 electrons, so I go from 1 to 2. Add my electron in my orbital diagram over here. Alright, so I'm going across, so I'm skipping over this D block gap that I have here because I don't run into it. So I kind of read the periodic table like a book. I go from left to right. So my next element, left to right, is boron. So when I write my electron configuration, I go 1s2, 2s2, 2p1. So I filled my first energy level, I started my second energy level, but I filled my 2s energy level. And I'm going over here to where my p block starts. So now I'm at second energy level, 2, p block, and I only have 1 electron that's in that p block. So when I look at my orbital diagram, I've got my 1s orbital diagram, 2s, but now I've got 2p. And because this 2p can hold a total of 6 electrons, I do have to show all 3 of these little orbital diagrams, or all these 3 orbitals within this orbital diagram for p. It's going to carbon. I'm just adding in an electron, and Hund's rule states that electrons are going to spread out into these different orbitals before they double up. So here's where we get a little bit of a change. So instead of my next arrow being down with the first arrow, when I built this p block section, it's going to go to this next orbital. So they spread out. So nitrogen then is going to go out one more. And notice that I'm still keeping this 1s2, 2s2, but I just keep changing my electron number here. So with nitrogen I have 1s2, 2s2, 2p3. So now all my electrons are pointing up. So you would expect that the next one is going to come back and go down. So now I have 4 electrons in my p orbital. And I'll keep adding to my p orbital until I get to 6 with neon. So we have oxygen here, fluorine here, neon here. So this fills my second energy level. Neon fills that second energy level. So I've got 1s filled, I've got 2s filled, and I've got 2p filled. Alright, so some things I want to talk about before I go into more advanced electron configurations. Talk about valence electrons. And the electrons, those are the electrons in the outermost principal energy level of an atom. So if I look at nitrogen here, my energy level outermost is 2. So my valence electrons would be 2 from this 2s and 3 from the 2p. So for nitrogen, I have a total of 5 valence electrons. With sodium, my highest or outermost principal energy level is 3. and I only have 1 3 in this example, so I only have 1 valence electron. And then the core electrons are the inner electrons that are not involved in bonding, so that's everything else. So sodium, my valence electron is 1, and everything else are my core electrons. So there's a nice neat trend to valence electrons, which would be good to make note of. As I go across the periodic table, I have 1 valence electron for this first group, 2 for the second group. Skip my D block because we do have variable valences. And I go 3, 4 where carbon's at, 5, 6, 7, 8. Alright, let's look at more complex electron configurations and orbital diagrams. So notice that I'm going to be looking at potassium, which is down here on my 4th energy level. And notice that I've filled quite a bit. So let's look at this first example. So 1s2 would have been hydrogen, helium. 2s2 would have been lithium, beryllium. 2p6 would have gone from boron to neon. 3s2 would be sodium, magnesium. 3p6 aluminum through argon. And then 4s1 is where I'm at with potassium. And my orbital diagram looks a lot like what I started with. So I have 1 orbital for each s, 3 for each p, so I have 2p here, 3s here, 3p here, and then 4s1 there. Alright, with calcium, I'm just adding an additional electron from potassium, so I go from 4s1 to 4s2. So my orbital diagram, I'm just adding this additional electron onto the end. Now, titanium is down here at number 22, so I'm now getting into this D block. So I've got a little change for us whenever we get into this D block. So we hit element 21, we're going from 4s2 where calcium was at, and we're dropping back an energy level with this first row of D block. So now I'm in 3D. So the number of electrons is just how many blocks I've gone over. But I'm now in 3D2 with titanium. So my electron configuration is now adding this D block. And I do have 5 orbitals within a D block. And I did spread out my electrons, because Hund's rule says so. Alright, with iron, I'm moving over in the middle of my D block, so element 26. I'm still here at my 3rd energy level, so it still is 3D, but now I have 6 electrons. Just count them over. 1, 2, 3, 4, 5, 6 electrons. So my electrons are spread out for the first 5. And then my 6th one comes back as a down arrow. Alright, and we'll wrap this up with germanium, which is way over in our P block. So I've gone through my D, and I'm going back to P. So from calcium at 4s2, I'm filling my 3D block, which should be 3D10. So I got a little edit here, just cross that out. It should be 3D10. Because we've filled this D block, which has 10 elements going across, or 10 electrons. And now I'm going back up an energy level, so this is back to 4, and it's 4P block, 2 elements over, so 4P2. So I filled my D block, I go down here, and I got 4P2. Alright, that ends our lecture on electron configuration.